Okay, hello everyone. Welcome. Can you see a slide that says lecture 4, maximum likelihood estimation? Give me a thumbs up if you can. Great, thank you. Okay, so we're gonna wrap up quickly with a little bit of stuff that we didn't finish last time, which was MLE for a Gaussian, and then we'll jump into today's topic. So let's finish this up first. So remember, the basic idea behind MLE is that I'm given a bunch of observations. For now, let's just assume that they're like simple like scalar measurements, like a bunch of heights that I've measured or something like that. And I'm going to assume that these measurements that I'm given follow some particular distribution, which I don't get to see, which is the thing that I'm trying to estimate. So here, for example, it could be a Gaussian with some mean mu hat and some variance sigma hat squared. And I just don't know what those values are. I don't know what mu hat and sigma hat squared are. I'm trying to estimate those. And I'm estimating them according to the data that I'm given. So what MLE, maximum likelihood estimation, suggests that I do is that I look for what I call the maximum likelihood estimate parameters. So theta MLE. And here I'm using theta, as a general term for parameters, but in this particular case, theta would denote, this mean and this variance that I'm trying to estimate. And I find this estimate of my parameters by maximizing the following. So I'm going to maximize the sum of the log probabilities of the data that I see for those particular parameters theta. Okay, so here in particular, right, let me actually just write this out as the mean and the variance that I'm trying to estimate. This turns into the sum over all the data that I get to see of the log of a normal distribution, right? The normal distribution probability density evaluated at my observation xi, parameterized by this mean and this variance, okay? And so how do we actually solve this? Well, the way that we solve it, right, is by taking partial derivatives with respect to both mu and with respect to sigma squared, and then setting those equal to 0. That's the way that we're going to try to solve this, right? So let's go ahead and try to do that. So trying to give myself as much space here to work with. What we had, right, was argmax over mu and sigma squared of a sum of the log probabilities of my observed data. If anything becomes illegible, by the way, just let me know. Or if anything's not showing up properly, just let me know. Don't want anyone to get confused by handwriting or technical difficulties or anything like that. You should only be confused by the things that I say. So for a Gaussian distribution, right, we can write this out a little bit more clearly, where what's a Gaussian distribution? It's like 1 over square root of 2 pi sigma squared, and then e to the, negative 1/2 x minus mu squared over sigma squared, right? So if I take the log of that, right, then, it's a product that turns into a sum, and then the exponent e to the whatever disappears because that cancels with the log. And then this thing actually becomes, right? And if you don't believe me here, you can, go work it out for yourself. But it becomes something that looks something like this. Actually, I'm going to run out of space here. So let me write this on the next line. Negative 1/2, I'm going to pull this out into the front. In fact, I'm going to pull it out of the sum of the thing that was inside the exponent, right, which is like xi minus mu squared over sigma squared, right? plus log sigma squared. This thing is actually still inside the sum, right? Plus something I'm going to call C. Okay, so what is C? Well, C, if you work it out, is something along the lines of like log 2 pi, or something times log 2 pi. But the reason that I'm calling it C is because I really don't care about it. And the reason that I really don't care about it is because what I'm trying to do here, right, is I'm trying to find a maximum with respect to mu and sigma squared, right? So if I have terms, additive terms, right, that don't contain mu or sigma squared, then they don't matter for this maximization problem. I could get rid of them and nothing about the problem actually changes. The argmax is still going to be the same, right? So I just write C to simplify my life because it doesn't really matter. And so in that way, I'm then able to, simplify the expression a little bit, which is going to be useful because what I'm trying to do here is, take partial derivatives and set them equal to 0. And I don't want all these extra terms hanging around, which are not going to affect the derivative anyway, right? So let's do that. Let's take some partial derivatives and set them equal to 0. What is the partial derivative with respect to mu? Well, I have only one term that actually has mu in it. It's this thing right here, right? And it's inside this sum, but when I take a derivative, the sum still pops out in the same way. And there's also this negative 1/2, which also pops out in the same way, right? Based on the rules of derivatives. So when I take the derivative with respect to mu, I'll still get this negative 1/2 sum over I. Remember, the sum over I is the sum over all of my observations, all of my data, right? And then the derivative with respect to this thing, right? Well, there's a 1 over sigma squared, which is going to, pop out in the same way. And then I have to use the chain rule to take this derivative, right? Which is going to be, 2 times the thing on the inside times the derivative with respect on the inside, which is negative 1, right? So actually, I'm going to get a negative 2, which is going to cancel out this whole thing right here, right? So I can actually forget about that entire negative 1/2. Still have this sum, right? The sum over I of xi minus mu, right, over sigma squared. And that's the derivative. So what do I do? Well, I set this equal to 0, right? So I know that for my maximum likelihood estimate of mu, this thing equals 0. So what does that mean? Well, if we work this out, we get that the maximum likelihood estimate is going to be equal to the sum of all my observations divided by the total number of observations, n. And this is just the empirical average, right? So if I asked you to give me an estimate of the mean of a bunch of observations, it'd be pretty weird if you didn't say just this, right? This is like the classic, canonical, obvious answer. And it's also the MLE answer, which is kind of nice. So maximum likelihood estimation looks like it's kind of doing something pretty sensible. Okay, let's try the same thing for sigma squared. So note here, I'm not taking a derivative with respect to sigma, right? I could do that too. Things just get a little messy. I'm taking a derivative with respect to sigma squared. So I'm treating sigma squared as its own variable, okay? If I take a derivative of this thing with respect to sigma squared, right? Well, I get kind of two things that pop out, right? There's this thing over here, which is, something times sigma to the negative 2. Or sorry, it's something times sigma squared to the negative 1, right? And so what that's going to give me is, negative 1 times sigma squared to the negative 2, right? Because again, I'm treating sigma squared as its own variable. And then this log sigma squared, if I take a derivative with respect to that, it's 1 over sigma squared, right? So the expression that I end up getting out here is something that looks like 1 over 2 sigma squared squared, okay? Sum, again, of my data points, minus, so I have 1 over sigma squared, but I have that times the total number of data points, right? Because this log sigma squared is inside the sum. So I get an n over sigma squared. N over 2 sigma squared, excuse me. Okay. So if I am looking for my maximum likelihood estimate again, so it's going to be, MLE here, right? Sorry for the tiny handwriting, right? Then I get that this thing is equal to 0 for the maximum likelihood estimate, right? Okay, so then setting things equal to 0 is nice, right? Because we can multiply out certain terms and then, work with something a little bit easier. So what I'm going to do here is I'm going to multiply this by this denominator, 2 sigma squared squared. Okay, so what happens when I do that? Well, this thing goes away, right? Because that's what I'm multiplying by. This thing you'll notice is, missing a term that's sigma squared, right? So if I had another sigma squared here, this would also be 2 sigma squared. So if I multiply this by 2 sigma squared squared, I'm going to get a sigma squared on the top. Okay. And then I can move that thing over. So then what I get is the following, that sigma squared MLE, right? Just doing some algebraic manipulations that we're not writing here on the slide, because the slide's not quite big enough, is equal to sum over all my data points of that observation minus the mean squared over n. So again, it's this average, right? It's this average it's this average difference squared, right? Which is also a very natural way that we might estimate a variance given a bunch of observations. Turns out this is actually something called a bias estimator. Maybe this is something that you've seen in other classes. And if I were to instead divide by n minus 1, I would get an unbiased estimator, but we're not going to worry about that. This is the maximum likelihood estimate, which seems, pretty reasonable, all things considered. Where does the divide by n come from in the maximum likelihood estimate of mu? Okay, so basically what's going on here, right? And I recognize that not everything is written out crystal clear on the slides because I would require a much bigger slide or a much smaller handwriting. But basically what's going on here is I can multiply everything by this sigma squared, right? And then I'll get sum of xi minus mu is equal to 0, right? So mu, you'll notice, doesn't actually depend on I, but it is inside this sum, okay? So I could also take this out, and what I get is n times mu, okay? So then what I get is that sum of all my observations minus n times mu is equal to 0, which is how I get this divide by n over here at the bottom. Oh, and I see someone else also helped answer the question. Thank you. Okay, so that is wrapping up our example from last time about how to do maximum likelihood estimation for a Gaussian. Today we'll get into some more stuff about MLE and some hopefully more interesting stuff, some more stuff that's directly relevant to machine learning. Okay, so what is today's lecture? Well, in last lecture and also just now, we introduced MLE. Which is, essentially a principle or a tool for statistical inference, and we gave an example of how that might actually look. Today, we'll continue this discussion, talk about some more properties that MLE enjoys, which are, kind of nice, at least theoretically, and also see its relationship to certain information theoretic concepts. So remember, in the math review lecture, we talked a little bit about information theory, like cross entropy, Kell divergence, things like that. We'll see how MLE actually relates to some of those concepts. And we'll see more specifically how MLE actually applies to machine learning, which is, what we're trying to do in this course. And then we'll start our discussion, which will continue, on Friday and also into next week about linear regression. And we'll start from the MLE perspective since we've already laid that groundwork for understanding things from an MLE perspective. So you may have seen linear regression before in one of your previous classes, but maybe you haven't seen it from this particular perspective, and it'll be nice to get multiple angles on the same thing because that'll help deepen your understanding of the concept. Let's talk a little bit about what MLE ends up looking like in the limit of infinite data. So what happens as n, our number of data points, actually goes to infinity? Well, remember that MLE is trying to solve this particular problem, right? right? It's argmax over my parameters of the sum of the log probability of my data, right? Now I could equivalently write this as 1 over n, so an average instead of a sum, right? Nothing actually changes about the argmax. I'm just dividing by something to make it look a little nicer. So instead of a sum, I'm now working with an average. But the argmax is still the same, right? Nothing about that changes. Well, as n goes to infinity, right? This thing becomes an expectation of the log probability. Oops. Log probability of x, right? Where x is sampled according to my data distribution, right? So this is an expectation with respect to the data distribution, which I can call, I think last time we said, we called it theta hat. So, theta hat represents like the true parameters that I don't know, right? And that's where my data is being drawn from. And then I'm trying to estimate what those, well, if I have infinite data, then the quantity that I'm trying to maximize is this one right here. It's an expectation of the log probability of, the random variable that represents my data. Let's open this up here. 1 second. Okay, there we go. Okay, so remember that we talked a little bit about Monte Carlo estimation as well in our math review lecture. And we basically said that, basically expectations are approximated by, these types of empirical averages, right? If I collect a bunch of observations sampled from a particular distribution, and then I average them together, that gives me what we call a Monte Carlo estimate of that expectation, right? More generally speaking, the way that we said it was that if I have, this quantity that I'm trying to estimate, it's the expectation under some distribution P of some function f of a random variable x, right? That this thing is approximately equal to the empirical average over n times that I sample x from P, right? And then, just running those through F and then taking the average gives me an approximation of that expectation, right? If the observations that I'm getting x1 through xn are sampled IID from P. And generally, we're going to say this without proof, but hopefully it's fairly intuitive. This gets more accurate with larger n. Okay, so as I collect more and more data and then take this average, it more and more closely approximates this expectation, which is the thing that I'm trying to estimate, right? So that is certainly nice. So all of this is to say that it intuitively explains, we won't, theoretically prove this because it's a little bit, out of scope, but it explains this particular property of MLE, which people call consistency. And basically the consistency property says that if I'm given large enough n, okay, so if I have enough data, what is enough? Well, it kind of depends on the particular thing that you're trying to estimate. But if I have enough data, eventually, if I collect more and more data, then if the parameters that I'm trying to estimate actually are in the set of parameters that I'm considering. So remember, this thing is a capital theta, right? It represents the set of parameters that I'm considering, like the set of all means and variances for Gaussian or something like that, right? If this is true, if my model is well specified, then theta MLE, my maximum likelihood estimate, will eventually equal theta hat, as in my maximum likelihood estimate will recover the parameters that I'm trying to estimate, the actual underlying parameters of my data distribution. So this is very nice, right? It says that if I can specify a model that accurately describes my data, and then if I can collect enough data, then what's going to happen is that MLE is kind of intuitively the right answer, in the sense that it will give me the correct set of parameters that actually explain my data distribution. So this is something that is very theoretically nice. It doesn't exactly tell us in practice what we should do, because we don't often have well specified models. Like, it's not often the case that this is actually true, right? Because the real world is complicated and the models that we use are simple. And sometimes this is tricky too, where how exactly do we collect a whole lot of data? Nevertheless, having this type of property of MLE is nice intuitive motivation for why we might want to do it in the first place. Let me go through one more slide, and then I'll take a look at some of the questions. Like I said, we want to relate MLE to some of these concepts that we learned about information theory, right? Well, I didn't exactly teach them; I just told you that they exist. Nevertheless, hopefully, you all know that they exist, and so we can talk a little bit about this. So recall the definition of this information theoretic quantity that we called cross entropy, right? What is cross entropy? Well, it's this capital H, right? And it's a function of two distributions, P and Q, right? And it's defined as the expectation with respect to P of negative log Q of X. I remember we tried to say a little bit about what this quantity actually means, and it's not, exactly super clean to describe, but on some level, it kind of tells us a little bit about how similar these two distributions are, P and Q, right? Because what we said, again, without proof, is that if P equals Q, then this quantity here just equals the entropy of P, right? And as it turns out, the entropy of P is the minimum value that the cross entropy can take on, which means that if Q differs at all from P, then this quantity, the cross entropy, is going to be larger than the entropy of P. And so in some sense, it kind of tells us a little bit about how similar these distributions are, because it grows as P differs more and more from Q. Okay, so that was our cross entropy value, or our cross entropy definition, right? Let's take a look at what happens if we plug in the data distribution and our model into this equation. So we have the cross entropy between, right, the distribution that's actually generating our data versus, some model that we have with parameters theta. Then what we get, right, just by, pattern matching the definition above, is the expectation with respect to P theta hat of negative log P theta, which if I collect a bunch of data, right, x1 through xn from P theta hat, then I can use a Monte Carlo approximation, Monte Carlo estimate, and say that this is approximately equal and, more accurate the more data I get to collect as n grows, right, of the empirical average of negative log P theta xi. Okay, this might look pretty familiar to some of you. It's basically just the log likelihood that we're trying to maximize in MLE, but negative, right? So if we're maximizing log likelihood, we would be minimizing this quantity. So therefore, maximizing likelihood is approximately equivalent to minimizing cross entropy. I say approximately because there's a Monte Carlo estimate stuck in the middle, right? Nevertheless, approximations aside, maximizing likelihood and minimizing cross entropy are actually the same thing. And so oftentimes in the context of machine learning, when people talk about maximum likelihood, they'll use the other phrase, which is they're minimizing cross entropy. So it's good to know what people mean when they say that. When people say that they're minimizing cross entropy, all they mean is that they're doing maximum likelihood estimation, whether or not they know it. There's also another way that we can interpret this, which is through KL divergence, which is almost the same thing. So remember the KL divergence, right, between two distributions. So here I'm going to plug in p theta hat, and remember there's this funny notation where I put two bars in between and p theta. Well, we wrote out the entire definition before, but the thing that's important here is that remember what we wrote about the KL divergence is equal to cross entropy minus entropy, right? So it's equal to the cross entropy of p theta hat and p theta minus the entropy of p theta hat. Okay, so this is kind of nice, right? Because remember what we said, like cross entropy kind of looks like similarity, but the minimum value is the entropy of p, which kind of makes things a little bit strange. The KL divergence, right? The minimum value is 0 because we're subtracting the entropy of p, right? So when p theta hat and p theta, or more generally p and q, when they're equal, the KL divergence is 0. Otherwise, the KL divergence is larger than 0. It's positive, right? So KL divergence is kind of nice because it's a bit cleaner of an actual quantity to measure distance, even though it's not exactly a distance metric like we talked about. But intuitively, it has that intuitive meaning, right? Where it's 0 if the distributions are the same, and it's positive otherwise. Okay. You'll notice here that this right here, right? Entropy of my true data distribution, p theta hat, right? It's a constant with respect to the parameters that I'm actually estimating or learning or fitting, right? Theta. So because it's a constant, again, when we do these types of maximizations or minimizations, we can throw out all of our constants, right? Because they don't change anything about the optimization problem. They're just cumbersome. So if I throw that out, then I'm back to minimizing cross entropy. So it turns out that minimizing cross entropy in this particular context, when I only have control over theta, is the same as minimizing KL divergence, which is also the same as maximizing log likelihood, right? Which is MLE. So that's how all of these different concepts kind of combine together into this giant soup. And you'll see, different people refer to the same thing according to these different concepts: maximum likelihood, minimizing cross entropy, minimizing KL divergence. You'll see these things all over the place. So it's good to know that, a lot of the times they actually refer to the same thing. Okay, so I'll pause here now. And if anyone has any questions, you're also free to, unmute yourself and ask. Otherwise, I'll also just be looking through the chat.
Wait, what does KL stand for again? Sorry.
It stands for callback liveler, just 2 last names.
Okay, thank you.
Mm-hmm. I thought p hat usually indicates an estimate, not the true parameter. That, yeah, and sometimes, I'm actually going to use hat to denote estimate and not the true parameter. The hat convention, for some reason, you see it quite a bit when we're talking about MLE. Try not to get too confused. I know that it's like a lot of notation gets jumbled around and used for multiple things. Hopefully, within the context of each particular thing, we can make it clear what we're saying there. Can you explain again what it means by log p theta xi? Why the log? So we took a log, remember, before we didn't have log, right? We had a product of probabilities, right? And the reason that we had a product was because we assumed that all of our xi's are independent. Therefore, that joint distribution, right, becomes a product of individual distributions. But a product of distributions is actually really difficult to work with, because what I want to do is actually take a derivative, right? And taking a derivative of a product of a bunch of things involves many applications of the product rule, which is just really unwieldy, right? So what we said is that instead of trying to maximize that product of probabilities, we can try to maximize that log of the product of probabilities, because an argmax doesn't change under the log function, because log is monotonically increasing, right? So argmax of f of x is the same thing as argmax of log f of x. Okay, nothing about that is actually different, right? The max value is different, but the argmax is the same, right? So when I say log product of probabilities that turns into a sum of log probabilities. What does p theta stand for? So theta are our current parameters, right? Theta is like the estimate of the parameters that I'm trying to get, right? So it's like, the mean and the variance that I'm trying to estimate for a Gaussian distribution. So after I specify what the family is, what the distributions are, right? Then p theta just denotes the actual distribution, right? So theta could be a mean and a variance, and then p theta could be a Gaussian. Does that help answer the question? I'm not sure if I fully understand the question. Can I repeat the last bit about minimizing KL divergence is the same as minimizing cross entropy? Yeah, okay. So, I'll answer the second question because I think that it'll encapsulate the first question. So what situation would minimizing KL be different from minimizing cross entropy? They would be different if this wasn't fixed, essentially. So, I don't know exactly what the cleanest example is, but, if I had control over theta hat somehow, I don't, right? But if I did, then this thing is no longer a constant, right? This thing becomes something that, can also change as theta hat changes. Therefore, this, KL divergence optimization problem will no longer be the same as the cross entropy because you're missing this term, right? The only reason they became the same is because I threw out this entire thing because it was a constant. And does that help answer the question? P theta is the model. Okay, so it's my estimate of the mean and variance, and p theta hat is the true data distribution. The actual Gaussian that my data came from. Assuming that it actually came from a Gaussian. In the last slide, how did you introduce the 1 over n term in the first line? Because dividing by a constant, n in this case, also doesn't change the argmax, right? These are all just, monotonic transformations that don't change the actual optimization that I'm trying to do. Therefore, I can just, essentially, throw them in as much as I want in order to make things more convenient. I see a question about concept shift, which I'm not exactly sure what that means, but maybe we can talk about that during office hours, which again, happened right after this. But in the interest of time, I'm going to keep moving now and talk about something that we really haven't touched on yet at all up until this point, which is what the heck does any of this have to do with machine learning, right? I've been telling you about MLE this whole time. I haven't told you a thing about what this actually means for machine learning, for example, for regression and classification, right? Well, what's the setup for regression and classification? I'm not just given a bunch of observations x1 through xn, right? I'm actually given input-output examples, x1 and y1, right? And xn and yn. Why am I given that? It's because I'm trying to learn a model that given x can predict y, right? I gave a pretty bad example last time of like given height, predict weight or something like that, right? It doesn't really matter exactly what the point is that we're given input-output examples, xi and yi, and we're trying to learn a model that goes from xi to yi, predicts yi given xi, right? Well, what we can do in order to try to set that up is actually basically use a very similar setup to what we already had, just with some slight differences. So if I'm given my data xi, yi, for I equals 1 to n, I can still assume a set of distributions on x and y. Now it's a joint distribution over x and y, right? Just like I did before. I'll denote that the exact same way, right? Where I have p theta for theta in some, family or set of parameters, capital theta, right? However, the way that I'm going to set this up when I have a machine learning model, right? A machine learning model, at least in this particular instance, all it cares about is predicting the output given the input, right? It doesn't say anything about where the inputs come from, right? I'm not specifying a distribution over the inputs. I'm only saying that I want to figure out how to predict outputs given inputs. And so the way that we actually encode that into our model is to say that this distribution here, this joint distribution, p theta of xy, I'm going to factorize it as P of X and then P theta of Y given X. Okay, so what is going on here? Well, basically what I'm saying is that my parameters theta say nothing about where X came from, all right? X came from some distribution P of X that does not depend whatsoever on theta. Okay, I can change my model parameters all I want. It's not going to affect the distribution over X. Okay, so X comes from some distribution P of X. As far as we're concerned, it's fixed. Okay, there's nothing that we can do to try to change it. The inputs are what they are. They're going to keep coming from the distribution that they're specified from. However, I do specify that I can control, or at least I can, try to model what is the distribution of my outputs given those particular inputs. That's P theta of Y given X, right? So the parameters here dictate this conditional distribution, Y given X, okay? So if I do this particular type of factorization of my distribution, then what does my objective or what does my definition become? Well, it turns out it's very similar to what we had before, just the math works out slightly differently, and it works out fairly cleanly too. So here I have, again, I want to estimate the MLE of my parameters theta, and that's still, this thing. It's still the argmax, right? Writing it out first without a log just to make things clear, right? Of the product of probabilities. But P theta of XY, right? We already said that it factorizes according to P theta, P of Xi, and then P theta of Yi given Xi, right? We already said that this is the way that things factorize. So this is what my product of probabilities looks like, right? And what I can do is I can, basically do the exact same trick that I did before. And like I said, we're going to do this trick, every time, right? Is I can take the log of this whole thing, and that does not change what the argmax is going to be. So I can instead work with a sum of logs. Well, log of what? Log of this thing, right? But this thing itself is two things multiplied together. So when I take a log, right, I get log of this plus log of that, right? So I get log pxi plus log p theta yi given xi. You can still see on the edge there, right? Okay, good. Yes. But you'll note one more thing. This thing, what is it again? It's a constant, right? It's a constant with respect to theta. There's nothing about theta that actually shows up in here. Therefore, based on my modeling assumption that theta controls nothing about the input distribution, right? This thing does not affect my optimization, right? Regardless of whether I have this or not, my argmax over theta is going to be the same, right? So I can, again, just throw it entirely away, and my argmax, my optimization problem stays the exact same, and I have argmax over theta of just the sum of conditional probabilities. So log p theta yi given xi. That's the final thing that I'm going to be working with, is I'm going to try to find a set of parameters, right, that maximize the log probability of my outputs given my inputs, okay? And remember, that's what we really care about in machine learning, or at least in this particular context, right? In this particular context, I have a model that's trying to go from inputs to outputs, right? What am I given as an input in order to try and predict? And what am I given as an output? What am I actually trying to predict, right? So when I try to find a model that has, good parameters, it kind of intuitively makes sense that I'd be trying to maximize this type of quantity here, right? Maximize the log probability that my model assigns to these outputs given these particular inputs. That's going to be the optimization problem that I'm going to trying to solve if I'm doing MLE in the context of machine learning, okay? And I think that kind of the way that we can try to make this a little bit more concrete and clear is to actually do a particular example. And the example that we're going to give is probably one that you've seen before. It's essentially least squares linear regression, but it's from the MLE perspective, which maybe you haven't seen before. Maybe you have, maybe you haven't. So the only reason that I put least squares in quotes here is because that is the solution that we're going to end up with, or the problem, the optimization that we're going to end up with. But we're coming at it from the MLE perspective rather than directly from the least squares perspective. So it's the same thing, just from a different angle that maybe you haven't seen before. Okay, so how does this set up? Well, set up in the same way that we did before. So assume that we're given data, x1, y1, all the way through xn, yn, right? X here is some d-dimensional vector, and y is a real valued scalar, right? So that's the regression problem. Right, we're trying to estimate a real value y given the vector x, okay? So we're going to assume that this output y conditioned on the input x is generated according to the following. So this is the distribution that we're going to put on y given x, okay? We're going to say that y given x comes from a Gaussian where the mean, right, is specified by some linear function on x. Okay, so it's given by some w hat transpose plus b hat. Again, right, we're using hat here in this particular context to denote some true underlying value of the parameter that we don't have access to. So we're trying to estimate it instead, right? So the mean of my output given my input is a linear function on the input, and then it has some variance sigma squared attached to it. And this is also kind of like a true, parameter value, but it's not something that we're going to try to estimate. And so we don't really care about it too much. Okay, so basically what we're saying, another way to write this, right, is that we could say that y is equal to w transpose x plus b plus some epsilon, right, where this epsilon, one more time, this epsilon, right, is distributed according to some Gaussian with mean 0 and then variance sigma squared, right? So it's kind of like noise. It's some kind of additive noise where on average the noise is 0, but it could be non-zero. We just sample from it, right? Okay, we don't need to specify the input distribution p of x. Remember, because it doesn't depend on theta. We assume that it doesn't depend on theta, right? And so it totally canceled out of the optimization problem that we had. So p of x could be, whatever we want. Even if we did specify it, it wouldn't show up in the argmax anyway. So we just save ourselves some trouble and we decide not to specify it. So then what we end up getting is the following objective, right? Argmax, right, over my theta. And I'll, write again, theta inside capital theta. But here, right, well, what is theta? Theta here are the parameters of my linear function that I'm trying to learn, right? I'm trying to estimate this w and this b because that's going to tell me the relationship between x and y, right? So theta here are my w and b. And then theta hat, right, represents all possible w and b, right? But what does that mean? Well, what is w? W is a d-dimensional vector, right? Because we're dotting it with x. And if x is a d-dimensional vector, then w has to be the same. W can be any d-dimensional vector, right? With any real values whatsoever. We're not placing any constraints on it. And then b is just a number, right? But b can also be any real value number, right? So that's the set of parameters that I'm searching over. And a member of that set is just a particular value of w and b, and we encapsulate that into theta sometimes for convenience, okay? What is my maximization problem? Well, it's the sum, remember, right? Sum of log probabilities of y given x, right? Well, in this particular instance, right, the way that I can write that is the sum of log normal densities, right? The normal densities of my observations yi, my observed outputs yi, right? Given what? Well, my mean right, is W transpose XI, W transpose XI plus B, and then I have some variance sigma squared, right? Theta, right, my parameters that I'm trying to estimate are the parameters of this linear function. This linear function defines the mean of how I'm going to predict the output given the input, right? So this becomes my mean. I have some variance, and then I'm just trying to measure, what is the log probability of my observed outputs given my inputs and these parameters that I've specified. And I'm trying to maximize that log probability, right? In order to try to learn the model that explains my data as best as I can, okay? Now, if I write out again the actual density for a normal distribution, right, and then I take the log of that, right, well, then a whole bunch of stuff cancels out, right, and then I get a log of an exponent just becomes the thing on the inside, right? So if I write this out, then what I'm going to get is something that looks like the argmax over theta. I'll stop writing capital theta because I'm getting a little lazy. Of the sum over all my data, right, of -1/2 sigma squared. Again, log x, it cancels out. So what I get is something that looks like W transpose XI plus B. Okay, this thing, right, is my mean minus my actual observations Y. That thing squared, right? Plus, again, something that's a constant, at least with respect to WRT, with respect to theta, okay? And that thing is, like log, something times log 2 pi sigma squared or something along those lines, right? And the reason that I say that it's a constant is because, we only have control over W and B. So if something doesn't show up with W and B in it, doesn't matter for us, right? It goes away in the optimization. Okay, so now we have something that's, this particular maximization problem. Okay, now what was the title of the slide? It's least squares linear regression. Okay, so if you've seen least squares linear regression before, maybe just as an objective or however else it was presented, it's usually just written as find the linear fit that minimizes this sum of squares, right? Here we have a max, but we also have a negative. So it's the same problem, right? So from the MLE perspective, what did I do? I assumed a particular distribution over my data, right? I assumed that I have some data distribution that's P of X, which is something I don't know and I don't care about. And then the conditional output distribution, Y given X, is a linear function plus some additive Gaussian noise, okay? And we'll also see next week why Gaussian noise is a pretty reasonable assumption in a lot of different types of setups. But that's the model that I assumed. And then if I start from that model and then I say, okay, how do I estimate my parameters within this model, MLE, and then I go through the steps, it turns out that MLE is the same as this least squares linear regression problem that so many people are so fond of, okay? And so we'll have a little bit more time next time to talk about linear regression, and we'll see how we actually set up that problem and then how we actually solve that problem. But I labeled this slide if time because I had a feeling that we wouldn't necessarily have time. So we'll save time for that next time. But I want to get through one more slide before we finish. And then again, remember, I have half an hour of office hours, so we can also take questions afterwards. I just want to mention that maximum likelihood optimization or maximum likelihood estimation typically requires what we call iterative optimization. What does that mean? Well, it means that for the examples that we've seen so far, we can actually obtain this estimate in closed form. Take the derivative, set it equal to 0, find an analytical solution, right? But we're going to see a lot of examples in this class for which this is not the case. And if it's not the case that we can do it analytically, we typically instead rely on something called iterative optimization, where we start from a particular guess of what the parameters might be, and then we continually refine that guess, making it better and better until we're actually satisfied, until we think that we've found the estimate that we're looking for. And this is, very broad and high level right now, but we'll talk in a lot of detail about what that actually looks like. One can take entire series of classes on how to do iterative optimization. And we'll start our more limited discussion of this topic in a couple of weeks, but just know that this is coming. Okay, so I will wrap up there. We got through most of what I wanted to get through today. And on Friday, we'll continue with our discussion of linear regression in particular, and we'll start from where we left off. Okay, so I have half an hour of office hours now, and I'll stop the recording and then take questions. Thank you.